Okay, so again, Sehyeok Park, Rutgers on correctly rounded math libraries that are rounding mode independent. Please.
Hello everyone, I'm here on behalf of the Rutgers Architecture and Programming Languages Lab to present our work on our RLibm project. The overarching goal of RLibm is to improve the portability of scientific computing. Scientific computing makes extensive use of math libraries, and for applications to be portable, the math libraries they use should ideally produce correct standardized results. And for this purpose, RLibm believes there needs to be correctly rounded math libraries. So I'll start off by explaining what correctly rounded math libraries are. Given a function and an input, the correctly rounded result is the output of the function evaluated in infinite precision, directly rounded to some target format using some rounding rule. So here's an example. Suppose v1 through v3 represent 3 consecutive 32-bit floats. And let's say for a given input x1, the log value evaluated in infinite precision is this value shown here. For the vast majority of their inputs, elementary functions like log produce irrational values that are not exactly representable in finite precision. In such cases, the real function result would need to be rounded. Under round to nearest, log of x1 would round to its nearest 32-bit float, and that would make v2 the correctly rounded result. A function that can produce correctly rounded results for all its inputs is a correctly rounded function. A math library consisting of such functions is a correctly rounded math library, and RLibm believes that that is the gold standard for reproducible numerical programming. Now, math libraries generally approximate elementary functions like log using polynomials. The most conventional approach to developing correctly rounded elementary functions is the minimax approach, which minimizes over all inputs the maximum error incurred by a polynomial relative to the real function results. In contrast, instead of approximating the real function results, RLibm proposes directly approximating the correctly rounded results. Given a function, each correctly rounded result in some final target representation, like 32-bit floats, is going to have a range of values in some intermediate representation with higher precision, like 64-bit doubles, that all round to the correctly rounded result. Such ranges are referred to as rounding intervals. Now, relative to the real function result, the size of a rounding interval is 1 up, or unit of least precision. You can think of the up for any real number as the distance between the two nearest neighboring floating point numbers. So in this example, the up of log of x1 will be the distance between v1 and v2. The key takeaway here is that an approximation can incur up to 1 up of error relative to the real function result and still produce the correctly rounded result so long as its output is within this rounding interval. Now, given this 1 up leeway, rounding intervals offer a large degree of freedom of tolerable error as it pertains to correct rounding. This large degree of freedom allows for approximation using low-degree polynomials with low evaluation overheads. Now, to utilize such rounding intervals, we need to have correctly rounded results to begin with. Fortunately, there exist math libraries like MPFR that can produce correctly rounded results for any arbitrary target representation. The negative is that the functions in such libraries can be a bit too slow to be used directly in programs, but nevertheless, they are suitable for math library development. Using the correctly rounded results provided by such libraries as oracles, RLibm identifies a more optimized approximation of those results using the associated rounding intervals. So in short, RLibm's motto is, give us your results, and we'll find an efficient way of reproducing them. So here's an overview of the steps that RLibm takes towards accomplishing this goal. So as alluded to earlier, RLibm starts off with the correctly rounded oracle results for a given function and the associated rounding intervals. I mentioned earlier that as long as its outputs are within these intervals, a polynomial can produce correctly rounded results. So the bounds on these intervals can be thought of as linear constraints on the expected outputs. RLibm encodes these constraints into a system of linear inequalities, and in doing so, it transforms polynomial generation into a linear programming problem. It then uses an LP solver to identify the appropriate coefficients that allow the final polynomial to produce values within the target rounding intervals. So this explains how RLibm produces correctly rounded results for a single representation. Given the variety of floating point formats that exist, it would be ideal to have for each function a single implementation that can produce correctly rounded results for multiple representations. And for this purpose, RLibm employs a non-standard rounding mode known as round to odd. Specifically, RLibm has observed that the correctly rounded n plus 2-bit result under round to odd is guaranteed to round to the correctly rounded result for any representation with up to n bits. By utilizing this observation, RLibm has become the first math library that provides for each function that it supports a single implementation that can produce correctly rounded results for all representations with up to 32 bits and for all standard rounding modes. For those of you who are interested in more details behind this technique, I would highly recommend reading the POPO 2022 paper. Now, despite RLibm's broad applicability, the correctness of its functions comes with a caveat. So let's suppose that an application, which could be running under any standard rounding mode, wants to use the RLibm library to obtain the output of log rounded to a 32-bit float. Here are the steps it would need to take. First, it would need to save its original rounding mode. Next, it would need to switch the rounding mode to round to nearest before invoking RLibm's log function. Then, it would need to return back to the original rounding mode before obtaining the final desired result. Now, RLibm's outputs can be rounded to the correctly rounded results under any standard rounding mode, but the functions themselves need to be invoked only under round to nearest. This is because RLibm performs floating point operations during polynomial generation, and while doing so, it uses round to nearest as the default implementation rounding mode. The rounding mode switch to round to nearest is required to avoid any rounding-induced variability, or any rounding behavior not observed during the polynomial generation process. But these frequent rounding mode switches are not without costs, and they incur additional latency for our final functions. To overcome RLibm's reliance on round to nearest and the associated overheads, we need to handle rounding-induced variability without explicitly setting the rounding mode. For this purpose, we have designed two new methods of developing correctly rounded functions that can be directly invoked under any application rounding mode. Our first method, rounding invariant outputs, accomplishes the goal by enforcing a single fixed implementation rounding mode within the code. Our second method, rounding invariant input bounds, accounts for rounding-induced variability during the process of generating the polynomials. So I will go over our rounding invariant outputs approach first. The goal of the rounding invariant outputs approach is to develop functions that always emulate round to zero behavior regardless of the rounding mode used by the invoking application. With respect to RLibm's functions, the primary sources of rounding-induced variability are the floating point addition and multiplication operations. To accomplish our goal of emulating round to zero, we develop custom addition and multiplication operations that always produce round to zero results. Now, to actually implement these operations, we need to address the following issues. First, we need to be able to ascertain under any rounding mode whether or not a floating point result conforms to round to zero. Now, we have affirmed that the rounding errors associated with floating point results can serve as appropriate indicators. And to utilize these errors, we employ error-free transformations, which are floating point algorithms designed to compute the rounding errors incurred by floating point operations. Secondly, given a non-round to zero floating point result, we need to know how to adjust its value accordingly. When the corresponding real arithmetic result is not exactly representable, a floating point sum or product will always return one of the two nearest neighboring floating point numbers. I mentioned earlier in the talk that the distance between two such numbers is 1 up. By definition, round to zero should always return the floating point neighbor with the smaller magnitude. Therefore, given a non-round to zero result, we can subtract 1 up from its magnitude to adjust its value in accordance with round to zero. So here is an illustration of how we apply these ideas in the context of our addition operation. So let's suppose one of our functions performs addition using the operand shown on the slide. Given these two operands, the real arithmetic result will not be exactly representable in double precision. Assuming that the current rounding mode is round up, a plus b will return the immediate floating point successor, and that number is represented by the value SOG on the bottom right. The value we want under round to zero, on the other hand, is the immediate floating point predecessor, and that number is represented by the value SRZ on the bottom left. So the task at hand here is to derive SRZ from SOG without any direct access to the real arithmetic sum or any explicit information about the current rounding mode. Now, floating point sums can differ across different rounding modes if and only if the real arithmetic result is not exactly representable. In such cases, a plus b would have incurred some amount of rounding error. To confirm the presence of this error, we apply two instructions that collectively compute a floating point approximation of the rounding error incurred by a plus b. Now, we prove in our paper that our error approximation t is non-zero if and only if rounding error exists in the initial floating point sum s. We also prove that when such is the case, the sign of t differs from that of s if and only if s has a magnitude greater than its real arithmetic counterpart. When both these conditions hold, we can conclude that the original floating point sum does not conform to round to zero, and we can subtract 1 up from its magnitude to adjust its value as intended. For our multiplication operation, we use error-free transformations to similar effects to utilize the rounding error incurred by floating point multiplication. Due to time constraints, I won't be able to go into our multiplication operation, but the algorithm and the associated proofs can be found in our paper. By replacing all the additions and multiplications in our polynomials with our new custom operations, we can ensure that our functions produce correct results regardless of the rounding modes used by the invoking applications. However, to apply this method, we need to augment each and every addition and multiplication with extra instructions that reason about the associated rounding errors. And these extra instructions entail additional overheads for our code. So given these overheads, it would be ideal to handle rounding-induced variability not within the code, but during code development. And this thought brings us to our second method, rounding invariant input bounds. Given an input and a polynomial, the goal of the rounding invariant input bounds method is to bound the full range of possible outputs obtainable across different rounding modes. Now, a floating point polynomial is essentially a sequence of floating point additions and multiplications. When evaluating polynomials, our original library assumed that all instances of rounding are round to nearest. For a rounding invariant outputs approach, we fixed the rounding modes to be round to 0. For a rounding invariant input bounds approach, we lift that assumption of uniform rounding and instead assume that each operation can be performed with a separate rounding mode. Now let's take as an example the following polynomial to be evaluated over the following input. And I'd like to quickly mention that the encircled multiplication and addition symbols represent floating point operations. So in the case that multiplication and addition are performed under round down, you would obtain the final output as shown on the slide. Now when these operations are performed under round up, you would obtain a different value. Given this variability due to rounding, the rounding invariant input bounds method represents polynomial outputs not as singular values, but rather as intervals. Now, with this in mind, we should note that polynomial outputs can be defined recursively. For example, the output of a polynomial p is either a constant or the sum or product of the outputs of two intermediate polynomials, p1 and p2. With the assumption of uniform rounding removed, the intermediate polynomial outputs are also rounding mode dependent. Therefore, we model not only the final outputs, but the intermediate outputs as intervals as well. Now, let's suppose that the last operation performed during the evaluation of one of our polynomials is a floating point addition. Under the rounding invariant input bounds method, the objective is to identify the rounding modes and the specific instances of the operands that either minimize or maximize the final output. It is a well-known property of floating point arithmetic that floating point sums and products are bounded by the round down and round up results. Naturally, the lower and upper bounds of the final polynomial output will involve round down and round up respectively. It is also well established that floating point sums and products are monotonically non-decreasing with respect to their real arithmetic counterparts. Given two intervals, we can identify the specific values that either minimize or maximize the sum or product using the rules of interval arithmetic. Based on the rules of interval arithmetic and the properties of standard rounding modes, we prove in our paper that the bounds on the outputs of operations always involve the bounds on the operands. Now, the operand bounds are just the bounds on the outputs of some previous sequence of operations. Given our recursive definition of polynomials, we can define operand bounds recursively in the same manner. With these definitions in place, we can once again use interval arithmetic to compute the final output bounds bottom up during polynomial generation. Now, doing so would require making some changes to our pipeline. If you recall, our existing pipeline ensures correctness by confirming that a polynomial's outputs are within the target rounding intervals. Under our new approach, we need to confirm the same property for both the lower and upper bounds of output intervals. Naturally, our candidate polynomials will be subject to a tighter set of constraints. On the flip side, if both lower and upper output bounds satisfy their associated constraints for all inputs, we can ensure that the final polynomial can produce correctly rounded results irrespective of the rounding modes used during evaluation. In summary, our new methods explore different trade-offs. Our rounding invariant outputs approach requires augmenting our functions with extra instructions that reason about rounding errors. The primary benefit of this approach is that the existing pipeline can remain largely unchanged. The only adjustment required is setting the rounding mode to round to 0 during polynomial generation. On the other hand, the rounding invariant input bounds method requires making extensive changes to our pipeline, as polynomials are evaluated in a different manner and are subject to a tighter set of constraints. Conversely, the resulting functions do not require any extra instructions to produce correctly rounded results. So using these two new methods, we have developed new implementations of the various elementary functions provided by our original library. So we've spent a fair amount of time into developing these functions, so it would really be nice if they are correct. And as intended, all of our new functions produce correctly rounded results for all inputs. And I like to add that the correctness proclaimed on this slide is an extension of the correctness already offered by RLibm. This means that using our new methods, we have developed functions that can produce correctly rounded results for multiple representations and for all standard rounding modes, while being directly invocable under any application rounding mode. Now, at this point, we should remember that the primary motivation behind this research was the performance overheads incurred by the rounding mode switches required by our original library. So we need to confirm that our new functions achieve meaningful performance boosts as well. So here is a graph showing the performance speedup of the rounding invariant outputs functions over their existing RLibm counterparts. And I like to mention that the latency of the original functions reflected in this slide contain the latency induced by the rounding mode switches. So as you can see from the bar on the far right, on average, the rounding invariant outputs functions achieve an approximate 1.5 times speedup over the original library. Now here are the results for the rounding invariant input bounds functions. On average, the rounding invariant input bounds functions achieve an approximate 2.3 times speedup. The speedup is more pronounced here because the rounding invariant input bounds functions do not require any extra instructions in the final code. Ostensibly, the rounding invariant input bounds functions perform the same set of core operations as their existing RLibm counterparts. Therefore, this result provides a more accurate depiction of the full degree to which rounding mode switches degraded the performance of our original library. In closing, we have designed two new methods of developing correctly rounded functions that can be directly invoked under any application rounding mode. Our first method, rounding invariant outputs, accomplishes consistent correctness by enforcing round to zero as the implementation rounding mode within the code. Now, round to zero is an efficient rounding mode used across various domains of scientific computing, so we believe that our custom operations can be broadly applicable aside from just developing math libraries. And our second method, rounding invariant input bounds, accounts for rounding-induced variability during the polynomial generation process. The resulting functions do not require any explicit rounding mode switches or any extra operations to produce correctly rounded results. Using this method, we have been able to improve the performance of our library by over 2x. And on that note, I would like to welcome everyone to try out our library, and I thank everyone for their time and attention.
All right, questions? Ganesh in the back.
From University of Utah. Really like this line of work. First of all, for GPUs, it's not possible to switch rounding modes. So I guess this method was needed in the first place. Am I right?
Yes.
Only for CPU, okay.
Yes.
Can you please describe the cost of generating the library itself? Does it change in any way? So say, consider you want a 64-bit implementation of the library. And let's say that for the CPU part, you did it the old way, and now you have to do it the new way. Is there any cost in generating the library that one perceives?
Yes, so I mentioned earlier that our new rounding invariant input bounds approach imposes tighter set of constraints on our polynomial generator. So our polynomial generator would take some more time under this approach. For the 32-bit target, the difference in time wasn't too noticeable. But I imagine if the output was expanded to 64 bits, we may see some larger overheads.
Has this been applied to 64 bits at this point, or?
Not yet.
Oh, okay. Thank you. Yeah.
Okay, another question?
Thanks for the lovely talk. I'm Alistair Donaldson from Imperial College London. I just wanted to confirm then, could you go back to the previous slide so I can remember the names of your different approaches? It sounds like the rounding invariant input bounds method is just superior to the rounding invariant outputs method. Is that right? As in, it gives you something correctly rounded and it performs better. So the first one is definitely intellectually interesting, and you said it could be useful for other functions, but is the takeaway that this input bounds approach is just the better of the two?
So that's a great question. So in my talk, I primarily talked about polynomial approximations, but elementary function implementations do a little bit more than that. For example, as a first step, elementary functions have to perform a process known as range reduction to enable the usage of low-degree polynomials. And these range reduction steps are essentially floating point operations as well, and they're also rounding mode dependent. And to ensure that our polynomial generators have singular inputs, we need to fix the rounding modes for range reduction. And for that purpose, we need to use our custom round to zero operations. So in short, our rounding invariant input bounds method requires the rounding invariant outputs method to a certain degree as well. So one is built on top of the other.
Oh, and but is there another question?
There is another question.
Super cool work. I'm Zach Tatlock from the University of Washington. One thing I was wondering, so you're kind of like using this error term from, two-sum, like EFT style stuff. Do you ever know anything about the order of the arguments? Like, can you use fast two-sum insights? And similarly, there's also, three-sum and other things. If you're doing the polynomial evaluation, can you use some of these larger adders, these in their error terms, to, fuse some of the polynomial evaluation steps and get more speed up?
So with respect to the question about the arguments, so I did not explicitly label it in the slide, but we're actually using fast two-sum, so we need to ensure that one operand is greater than the other. And with regards to your question about extending it to three sums, etc., I think the broadening of the various error-free transformation techniques and applying them would require more analysis on how certain polynomial coefficients could allow for such applications, and etc. And that analysis is future work. Yeah.
Okay, let's please thank Sehyeok.